In this presentation, we will discuss the conceptual design, performance, and stability analysis of a remote-controlled electric-powered aircraft. The design is intended to meet the requirements outlined in the project description, namely to carry a 1 kilogram payload while maximizing endurance and minimizing weight and adverse stability effects. Design layout and initial sizing. A constraint analysis was performed to determine the required wing area and power to meet the aircraft's performance requirements. Specified performance parameters included cruise conditions, level turns, takeoff, landing, and climb rate. All parameters were set based on a review of similar high-endurance aircraft and gliders. Following the first iteration, a preliminary CAD drawing of the aircraft was completed to obtain a more accurate estimate of the weight. The constraint analysis was rerun until converging on an initial design point for wing loading and power-to-weight ratio. Following our performance and stability analysis, our final design point consists of a wing loading of 8.49 kilograms per meter squared and a power-to-weight ratio of 0.04 kilowatts per kilogram. Given the wing area and power required, we conducted a preliminary geometry sizing using the methods outlined by Gudmundsson and Raymer in their aircraft design textbooks. And finally, following the stability analysis, we reiterated on this initial size estimate to obtain the final layout and size demonstrated in the table on the screen. Airfoil selection. Given the project requirements, our ideal airfoil should have a high enough CL max to provide sufficient lift, low CD min to reduce drag, and maximum CL over CD ratio to provide optimal gliding characteristics at cruise. Early in our design, we decided that we would disregard the commonly used high-lift airfoils for RC aircraft, such as Sealig 1223 and Epler 423 airfoils. Their high camber and high lift characteristics result in very inaccurate estimates for drag and are not compatible with the analysis tools and equations that we are using from the textbooks. So we opted for a more appropriate option suitable for a glider and ended up choosing the AG24 airfoil developed by Mark Drella. It's a commonly used airfoil in RC gliders and provides a design with a sufficiently large CL over CD ratio. For wing aspect ratio, we decided to go for a value of 35, which was chosen to closely resemble a typical glider and provide our design with very efficient aerodynamic flight characteristics. Our major design driver is to maximize endurance, and so a large aspect ratio will help to keep drag to a minimum and target the minimum power condition for endurance. For our fuselage, we mainly ignored any contributions from the fuselage in our performance and stability analysis. However, in order to maintain a realistic design, we did opt for a tadpole fuselage shape similar to most gliders to minimize drag. And finally, for the empennage, we conducted a preliminary tail sizing using the methods outlined in Gudmundsson's textbook. We used standard horizontal tail and vertical tail volumes for sailplanes, and our final tail design was determined following the stability analysis.
The bulk of our performance analysis has been done through XFLR5. We have also used MATLAB to calculate the endurance and range values and values for minimum and maximum velocity. SolidWorks was used to estimate geometrical properties such as span, area, and inertial properties. For XFLR5, the analysis was run at a fixed velocity of 15 meters per second, which is our cruise velocity, using the VLM method, excluding the fuselage as recommended. This provides the following polars. As you can see, at a CM of 0, we have a CL of 0.62, which is as calculated for our cruise velocity. At this angle of attack to trim, we have a CL over CD ratio of 227, which is very high and comparable to most high-performing gliders. And we have a CL to the power 3 over 2 over CD value of 21. For endurance, as this is an electric battery-powered aircraft, we cannot use classical relations for estimating the endurance and range of the aircraft. Instead, we follow a similar method which equates the power required for a steady level flight at our given cruise velocity. We employ two methods of calculating this power required. One is from an empirical relation calculated in the paper we have cited, which takes into account varying current rates for a battery. This gives us an endurance of around 12 hours. The other method involves using eCalc, an analysis tool, which will give us values of current and voltage and thrust at various RPMs using our motor, propeller, and battery specifications. We see that at cruise velocity of 15 meters per second, we have a drag which is around 1 Newton or around 100 grams of thrust. eCalc shows that at this values of thrust, we have around 0.4 amps of current, and this leads to another estimation of endurance, which is around 13 hours. Because they're similar, we believe the estimates are accurate. However, we have to take into account the fact that this excludes takeoff and landing, which will require more power. Also, any real motor will not be able to run at 0.4 amps. It will draw much more current and lead to inefficiencies. range is simply calculated as velocity times the endurance. And again, this leads to a very unrealistic value of 650 kilometers, and the same caveats above apply here.
For the minimum velocity, we used the AG24 airfoil data to select the lift coefficient occurring at 10 degrees. This value of 1.2 was substituted into the following formula to find the minimum velocity of 10.59 meters per second. For the maximum velocity, we used eCalc to find the DC current rating of 65 amps for our motor. Then we found the maximum available thrust to be the corresponding thrust at this current rating. Using the drag polar of our aircraft, we found the maximum velocity using the equation on screen by subbing in the drag value of 47.88 newtons, such that there is no excess thrust available. The velocity found to be 314 meters per second is considered to be quite unrealistic because the motor would likely overheat at such high current ratings. Also, the structural integrity of the aircraft would likely break down far before reaching such high velocities. For the absolute ceiling, we first took the climb rate equation of our aircraft and then found the relative density. We then used this relative density and found the height, assuming that we were flying at the troposphere. By using the range of power values that were provided by the battery using eCalc, we managed to create this following graph using MATLAB. Even though our absolute ceiling is shown to be 40 kilometers, it is unrealistic as the battery would never be able to supply such high current values due to overheating. However, at more realistic values, we see that the required ceiling of 150 meters can be met as long as we provide a value of 15.2 watts from the motor. For the climb rate, the same equation was used again. This time, for the power values, we used the more realistic values of 10 to 25 watts provided by the motor. We found that the climb rate would vary between 0.2 meters per second to 0.79 meters per second at sea level density.
In this section, we'll do the stability analysis of our design. We'll be concentrating on the self-correction capabilities of the aircraft to gain stability once it is in an unstable position, and we'll assume that there is no active control to bring the aircraft back to stability. Starting with static stability, we look at longitudinal stability. We'll follow this chart over here, where it gives you the condition that the derivative of the pitching moment with respect to forward speed, vertical speed, pitch rate, and vertical acceleration should have a negative sign, and that is what our longitudinal derivatives show over here. That means our aircraft is longitudinally stable. Coming to lateral stability, we follow the same kind of procedure. This chart gives you the conditions, the roll moment derivative with respect to side slave, and the yaw moment derivative with respect to side slave should be negative and positive respectively, and that is what our lateral derivatives show over here. Moving forward to dynamic modes, we start with the short period pitching oscillation. We expect the iron value to be negative and have an imaginary term to represent the damping and the oscillation. That is what we see over here. And if you see over here from our graph of pitch rate versus time, how quickly the system comes back to equilibrium. We also know that the altitude will be constant in SPPO mode, and that is what is shown over here in this graph. Then moving on to phagoid mode, there is slow damping in there, so the iron value would have a small negative term, and there's also oscillations. We expect an imaginary term over there. That's what we show over here, and you can see these graphs of forward speed versus time and pitch angle versus time, and see that slow damping and oscillation, but you see that the peaks are eventually killed off, but it takes a while. Coming to roll subsidence mode, we expect heavy damping, and thus our iron value shows negative value, a very large negative value. And from these graphs, we can see how quickly it comes back to equilibrium position, which is under 1/10 of a second. And then the Dutch roll mode. So there is oscillation in this mode. There's also damping in this mode, fairly large. And we expect the iron value to have a negative value and an imaginary value, and that is what we have over here. Now, looking at these graphs, we can see the oscillation in the initial stages of the mode, and then how it just dies down and brings the aircraft back to stability. So, and another way to judge the stability of the aircraft is looking at the Roth-Lucas graph of the longitudinal modes and the lateral modes, and these are two graphs. And so the poles in these graphs are the iron values of each mode, and they are all in the open left-hand plane, which shows that our systems are BMO stable, and they also signifies what to be expect physically from these modes. So, in summary, our aircraft is statically and dynamically stable.